Welcome, faithful followers, or junior masochists. I'm never quite sure what to address you as. But this particular section of the net ionic equation reactions, which, as we well know, is question number 4 on the free response. We know it's coming. It's the fastest 15 points on the test. I want you, by the time April rolls around, I want you to consistently be getting double digits out of the 15 points. Make sure you get 10, 11, 12. My students pretty much had an average of about 13 to 14 walking in as a class. There's always, somebody who can't memorize something, but you know what? It's okay, because you don't have to get a perfect 15. If you can bust the mean on this, which typically over the last 30 years has hovered around 7, occasionally nudging toward 8, with the exception of last year. Last year there was a ridiculously easy set of net ionic equation questions. I wouldn't expect that this year. I just wouldn't. That particular set was everything that I tell you to lay in bed the night before the exam and pray for. Now, this particular part scares the bejesus out of most folk, and it's because we don't really teach complex ions within any of the typical chapters that we cover. This is something that's like way back in the back of the book, and it's all full of theory and all kinds of scary stuff, but honestly, this is just an introduction. It's just a survey course, so let me demystify this for you. First of all, I have to tell you my personal opinion. This is my favorite because it is easy, and it's like a puzzle. And by the time you learn how to name this stuff and write this stuff, you just sound all smart. And in my world, that means something. So the big idea here is that we have things that you've been learning are insoluble. Solubility rules, right? If it's insoluble, then less than 3 grams, by most definitions, dissolves in 100 grams of water. Well, how do you ever get something like that to dissolve? Well, if it doesn't dissolve in water, you try an acid or you try a base. And if you try both, one of them's going to work. Maybe not both, but one of them's going to work. And what we really do to get that to dissolve is that there's a complexing that's going on. And so often it's a heavy metal bad guy, a silver, a mercury, a lead, but it can be zinc, it can be aluminum. There's all different sorts of metals, copper, iron, that will complex as well. But the big idea is, if water doesn't dissolve it, what will? Try an acid, try a base. And so you're going to pick up on some patterns as we go through this. And there are many patterns, and patterns are what make things easy, because students love algorithms. I have good news for you. There are lots of algorithms in this next section that we're covering. If you've ever asked a teacher, will it always work that way? Then you are a student who enjoys a good algorithm, because you don't want to have to think new and unique thoughts on every single problem that comes your way. You search out patterns. That's what all good scientists do anyway, is search out patterns and then embrace the patterns and apply them. So we're going to start with some nomenclature, because that's what's sorely lacking in your textbook. And if you are in a NIMSI school, a National Math Science Initiative school, your teacher has had the opportunity to go to laying the foundation training for pre-AP, the first year course. And there is a lesson in there on nomenclature. I taught nomenclature at the very beginning of the year, but I didn't teach this nomenclature until we got into the spring, because it is easy. It's kind of fun. It's like figuring out a puzzle, and students kind of hit a slump around February when the weather's icky and there's been snow and ice, and it's just not a good time to get outside and feel all energized by the sun. So it was kind of fun to take a little bit of a break and do something that was easy-greasy like this, and then come back to it. So nomenclature is the easy part. And then we're going to actually see that the equations may actually be even a tad easier. Now, the good news is that no one's going to ask you to name. Well, I take that back. I have seen a couple multiple choice questions, but it's rare that they ask you to name one of these complexes. But you do have to decipher names of these complexes, so it's important to be able to be literate with this. So what is a complex ion in the first place? Well, it's a combination of elements that come together to make an ion, and the combination is going to have a central metal ion. I'm sorry, yeah, that's right, a central metal ion, where the Roman numeral is going to tell you the charge. Even the things that you are not used to putting Roman numerals on, such as aluminum and silver, cadmium, and mercury, or not mercury, sorry, silver, cadmium, and zinc. You usually don't put a Roman numeral on those, but we do always put a Roman numeral on these. So it's going to feel a little weird at first when you do that, to things you've never put a Roman numeral on before. And then it's going to have another clump of of elements added to it that we call a ligand, and I realize that's a new word for you. Don't freak out over it. Ligands are basically the polyatomics that you already know and love, along with some halogens, along with water, along with ammonia. And so there's nothing mysterious about them. We just have a word for them, which is ligands. So they're behaving kind of the same way a polyatomic ion behaves as one species, but they may or may not have a charge, because we have neutral ligands and we have positive cation ligands and we have negative or anion ligands as well. So the ligand, very simply defined, is just a group that's bonded to that metal ion. What we are making, if we combine ions together, one of which is complex, one of which may or may not be complex, we're going to end up making a neutral compound. So this is just a neutral compound that contains a complex ion or two. So we get these scary looking things. Now I know that you're used to at this point for the square bracket to mean concentration and molarity, but in this particular setting, it doesn't mean that. It means, ooh, look, there's a metal inside. Ooh, look, it's got other stuff with it. This is a complex ion. So this particular complex ion must have a 3+ charge total. How do I know that? Well, it's with chloride. And what do you know chloride's charge to be? Yep, -1. And it took 3 of them to make that happen. So I'm going to work backwards and dissect out what's going on inside these square brackets. Ammonia is your good buddy NH3. It is neutral, right? It doesn't have a charge. It's just an ordinary molecule. It's a classic weak base. But when we put it into this situation, we change its name to amine. A-M-M-I-N-E, like ammonia, but not to be confused with amine as in amino acid, which is an NH2 group. That's another lesson. So this is hexa, because there's 6 of them, amine, because that's the name of that ligand, cobalt, and it would be cobalt Roman numeral 3, because the only way this entire set of brackets has a +3 charge, when this is 6 zeros, is that this has to be a +3. So again, we would name it hexa, amine. I know it feels weird to have 2 A's and 2 M's together in a word. Hexaamine cobalt, and this is all squished together in one word. Cobalt, Roman numeral 3 for the charge on the cobalt, not the charge on the overall thing always. I don't want to plant a misconception here. This is a +3 overall because these are neutral ligands with 0 charge. But that Roman numeral right here goes only to the charge on the metal inside. They just happen to be the same in this example. So hexaamine, cobalt, and then chloride. So this is just ordinary. That's not a complex. So we're going to have a nomenclature lesson before we come back and talk about the more common things that we see on this question. So I have to give credit where credit is due, because I would say I stole this, but I don't think you can steal something that you wrote. There's that company I referred to called Laying the Foundation. It's a teacher training program for pre-AP, grades 6 through however far we have to go before we hit AP. In English, that would be through 10th grade, because you know you have AP Language in 11th and AP Lit in senior year. So this particular lesson is the nomenclature lesson that I'm hoping first-year teachers are starting to use. Teachers of first-year chemistry would probably be a better way to phrase that, not their first year to teach. And this is a slice of that, along with a slice of organic nomenclature about alcohols and anes and enes and ines, oh my. And we won't do that in here. But these are actually kind of fun. So like I said, my kids would have learned a lot of nomenclature before they ever got to this, but we did this in the spring. It's just something that was sort of like a fun puzzle thing to do. So the rules are really simple, and you're going to like that, and you're going to feel like you're speaking chemistry. You're going to sound all smart and educated. You can impress your slacker friends with this newfound knowledge. So, like I said earlier, square brackets are used to enclose the complex ion or neutral coordination species. A complex ion, as defined earlier, is composed of a single central atom or ion with other atoms or molecules attached. The atoms or molecules that are attached are known as ligands. I know that's a new vocabulary word for you. The number of ligands attached is called the coordination number. It's often twice the oxidation number. Some coordination numbers are noteworthy in terms of memorizing when you go farther, but we're not going to worry about that. We're going to kind of take a shortcut that I'm not particularly proud of, but it works. And that is that if we double the oxidation number on the metal that's in this complex, then we're always going to form a complex that will exist. It may not be the most common, it may be rare, but it's at least a simple pattern, again, algorithm for you to follow. So again, apologies to the true analytical chemists who are going, that's not the most common. I know. Cut a girl a little slack. We're just trying to introduce something new to kids. All right, so coordination number of the complex ion. So again, that's how many ligands did you put? So it's just simply the number of ligands. Even numbers are more prevalent than odd numbers. So 2, 4, 6 are probably our most common. Now, the naming of complex cations and complex ions, anions rather, is similar, except, there's always the exceptions, right? Anions are always made to end in 8. So anion starts with an A, and we end with the prefix starting with an A, the 8. Coordination compounds, like other ionic compounds, are named with a cation first, preceding an anion. In other words, we still do a plus minus. That's what that's trying to say. And then here come the rules. There aren't too many. Aren't you glad? And you already know half of them anyway. So the rules for the naming of these compounds are as follows. As with any ionic compound, the cation comes before the anion. Check. You already knew that. In naming a complex ion, the ligands are named before the central metal ion. So metal last. In naming ligands, we add an O. And so that's added to the root name of any anion. For example, halides, chloride, bromide, fluoride, etc. become fluoro, chloro, bromo, iodo. That one's my favorite because it's fun to say. Hydroxide is hydroxo. Cyanide is cyano. Nitrite is nitrito. Nitrate would be nitrato. Get it? It's kind of fun. If the ligands are neutral, then we omit the O ending. And you don't have to worry about more than 2 neutral ligands. That's going to be water, which is going to be aqua, and the ammonia we just talked about, which is amine. So neutral ligands take the name they normally use as neutral molecules, but there are 4 exceptions which you must memorize. Really 2. H2O is not water in here, it is aqua. NH3 is not ammonia, it is amine with 2 M's. And that 2M spelling, like I said earlier, is so that you never confuse it with the functional group in organic chemistry that's NH2, as in, and single M amine group, as in amino acids, which you've heard of. Now, these 2 have never shown up on the AP exam, but just to complete your education, CO is named carbonyl, and NO is named nitrosyl. So those 4 require some memory work. But if you can lock on to aqua and amine, which aqua shouldn't be all that big a stretch for you with water, right? And then amine sounds like ammonia, and ammonia has 2 M's. This amine has 2 M's as well. Now, the number and kind of each ligand is specified by a Greek prefix that you already know. Mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. You're not going to get that big, but you get the idea. So you already know that. So the oxidation number of the central atom is designated, like I said earlier, by a Roman numeral in parentheses. When more than one type of ligand, okay, this one's a little bit tricky, more than one type of ligand is present, they're named in alphabetical order with no regard to their prefix. So in other words, amine comes before aqua because M comes before Q. They both start with A, get it? M comes before Q in the alphabet. So alphabetical order by name, not by symbol. If the complex has a negative charge, like we said earlier, we put this 8 ending on it, and we add that to the name of the metal. So when a Latin symbol is used for the metal, and you know which ones these are already, because these are the ones that were just a booger bear for you to originally master. Sodium comes to mind, right? Na. Iron. Fe. The ones that made no sense alphabetically to you, those are the ones that we're on the lookout for. They take on their Latin name because that's where their symbols came from, because they've been around so long. We've known about the older elements that we've known about for centuries. So they take on their Latin name in complex anions, but not in complex cations. That's going to take a little bit of practice to master. So the 8 ending that we're going to add to it is for anion. But again, they both start with A, right? Anion, negative ion, and A, 8. So it's like a signal going, ooh, negative complex. So, for example, tetraamine with this copper thing going on and a 2+ charge is called tetraamine, because we name the ligands first. Copper, Roman numeral 2, because it's a +2. But if I switch to a copper complex that's negative, this one is hexa, because there's 6 of them. Would be cyanide, but we put the O on it, so hexacyano. But I revert back to what copper really got its symbol from, which is cuprous, cupric, cuprate in this case. So cuprate. Roman numeral 2 is the charge on this ion. So it's a little bit of a math puzzle. You know that cyanide is -1 if you know your polyatomic ions, and there are 6 of them. For this complex to have a -4 charge, you have to work backwards and say, okay, what did I add to -6 to come up with -4? That was a +2. So that's where this is coming from. So this is a positive, so it will have aluminum in the name, but you're not used to putting a Roman numeral on that. So here again we have hexaamine, that's 6 zeros, so that you know that aluminum is +3, so that's where the +3 is coming from. When you add it to 6 times 0, that's still +3. And so this one would be called hexaamine aluminum, but you're not used to putting that Roman numeral 3, the charge on the metal. Not the charge on the complex, she says again, but the charge on the metal. All right, then this thing is negatively charged, so it's going to end with aluminate. Still Roman numeral 3. But this one is tetra, and that's hydroxide, but you call it hydroxo. So tetrahydroxo aluminate Roman numeral 3. Tetrahydroxo aluminate Roman numeral 3. Am I making your head spin? Because you may want to stop right here, and you may want to rewind to the beginning, and you may want to listen again. I'm going to go over it again if you're going, I kind of get it. So if you kind of get it, hang with me. Remember that you can stop at any time and go, whoa, 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 rewind and do this over. So here are some common neutral ligands. Again, I'm going to highlight the ones that are important for you. These two. Aqua and amine. Not that you won't ever see carbonyl or nitrosyl. I hope you have enough exposure now that wouldn't throw you for a loop, but there's CO and NO. But carbonyl and nitrosyl exist, and they're very common, but not common to the AP exam. Then we have common anion ligand names. So here are all of my halides, and you get one little brain cell spent to remember that you just don't call them fluoride, chloride, bromide, iodide. You call them fluoro, chloro, bromo, iodo. No one's going to ask you to pronounce it. Okay, so if you say it funny, it's okay. I may say some of them funny too. Then you know your good buddy hydroxide, it becomes hydroxo. You know cyanide, it becomes cyano. If you don't know SCN yet, as thiocyano, you will, because you will do an equilibrium lab with that. And then the last two are not as important. So all of these so far are important. So these last two you won't run into very often, but one of them is my personal favorite, if you've never heard me say that. Everybody needs their favorite polyatomic ion. Mine is oxalate, because I think it's fun to say, oxalate. And so I really like to say it oxalato. So when it becomes a ligand, it's oxalato, and it's oxalic acid. I just think it's kind of fun. Get your own favorite. That one's mine. It's taken. Thiosulfato is up for grabs. So if you like thiosulfate, that one's kind of fun too. You won't see those very often. I think oxalato might have shown up once in the last 30 years, but you'll remember it just because it's my favorite. And then these are those symbols that you had a hard time mastering. Remember when you were a Chem 1 baby and you were just learning even the periodic table? These were hard for you to remember. So Fe, Cu, Pb, Ag. I always thought G should be with gold, but I have to think and remember that it didn't get the G, even though that would make more sense to my English-speaking alphabet brain. It's Au for gold, and then 10 is Sn. So that translates if you are using anionic complexes. Otherwise, it's aluminate, etc. That makes sense. But these are the ones that may throw you for a loop if you see them in print. Ferrate, because if you think about Fe, cuprate, plumbate. So I have to tell you a story. You can fast forward through the story if you want to, but sometimes I think stories help you remember things. I'm a nerd. I've been a nerd pretty much since 3rd grade when I figured out what a nerd was. And that word wasn't around, but they had very unkind terms for people like me. And even though I have social skills, because I was raised an only child and had to learn to make friends quickly if I were going to have any friends at all, I still am a geek to the core. So my husband is a computer guy, but he fancies himself not a computer geek. He fancies himself more of a businessman in the computer world with like marketing and stuff. So in 1992, we were sent to England to live there for a couple of years. He got a really good job as the head of marketing for a European computer software firm. And we go to France for the first time. Never been to France. I'm very excited. But if you live in England, there's this thing called the channel that separates, the English Channel separates you from the continent of Europe. But it's like an hour-and-a-half ferry ride. So you drive your car onto this big ferry boat, and an hour and a half later, there you are. You're in France. You're in Calais, France. And in about another 2 hours, you can be in Paris. It's way cool. I live in Texas where it takes like 8 hours to drive to Corpus Christi to see my dad. So this is no big deal to me to go 3 hours to be in Paris, for crying out loud. So we have our our car that we have. It wasn't a rent car. It's the car we had in England, which means we're driving on the wrong side of the car. And now we're in a country that drives on the proper side of the road, in my opinion. So we eventually need to get gas. And so we don't speak French, stupid Americans that we are. So we go up to the gas pump and we ain't Kansas anymore. We aren't in Texas. We aren't even in the good old US of A. We are now in France, where leaded gasoline still exists and can ruin our car. We figured this out because the pumps look scary, and the nozzles are different. You know, in this country, when we made the transition, we were smart enough to make the nozzles different so that a bozo couldn't put the wrong gas in the wrong car when we were transitioning off of leaded gasoline back in the late 70s. Oh no, this is not how it works in France. So I'm saying, okay, let's think this through. We're just staring at the pump, staring at the pump, staring at the pump. Well, finally I see the fine print under the big yellow sticker with the octane, much like we have in this country, with the octane count, 83, 90, whatever. And I look at it and it says sans, which I did not know what that meant, but my husband at least knew that meant without. Though it said sans plum. And I said, sans plum. And he goes, well, sans means without. And I'm like, well, plum means plumbus. It means lead. This is the without lead. This is the unleaded one. We were feeling pretty proud of ourselves, these stupid Americans that speak no French. So you never know when little things like this will come in handy. And that's why it has the symbol PB. All right, story's over. Argentate, aurate, stanate. So you do have to put a little effort into learning those. So let's practice. I love practice. I either give you the name, you give me the formula, or I give you the formula, you give me the name. You ready? Let's try it. The best way for this to work is that you pause right now and you try the first one. I'll teach you when you come back, but you pause right now. Don't be a cheater. You know how I feel about that. Put me on pause. I'll wait. Still waiting. All right, let's give this a shot. When you're looking at a name, start here. It's 8. That means I'm going to have a negative complex. So whatever I'm going to put in those brackets, it's going to bear a negative charge. Could be negative 1, 2, 3, 4, 6. Who knows? The Roman numeral 3 is the next thing you want to look at. And you want to go, oh, that's my good buddy aluminum anyway, so that one's not too tricky. So put the metal in first, and then put your parentheses where the ligand is going to live. So my aluminum is a +3. I know that from that Roman numeral. Roman numerals are your friend. And so then I come back to the beginning and I say tetra, that's a prefix of 4. So there's going to be 4 on that parentheses. And what's inside it is hydroxo, which is OH. And I know that that's the hydroxide ion with a -1 charge. So if I have 4 negative ones and a +3, indeed, I end up with a -1 charge for tetrahydroxo aluminate, Roman numeral 3, ion. Now the next one gives you the formula and you have to come up with a name. I'll wait. Go ahead. Pause. Seriously, you need to work these out yourself. Give it a shot. It's okay to be wrong. Everything I know because I did something wrong. That's how you learn. Okay, so here I first noticed that it's positive. So I'm not going to worry about argentate. It's going to be silver when I get done. And you know that silver only has a +1 charge, right? So it's going to be silver Roman numeral 1 ion at the end. So let's get the front part worked out. That's a prefix that means 2. di. And then this thing inside is ammonia, but we write it amine. A-M-M-I-N-E. This all runs together. So diamine silver Roman numeral 1 ion. So all of this in blue until you hit the end of that Roman numeral, that's all one word. So it really feels kind of spiffy. All right, so how did I know it was a Roman numeral 1? I know that 2 times 0 is 0, and this is bearing a total charge of +1, so that has to be a 1. Plus, I know that silver's a 1. Always. How about this thing? Another ion, they give me the name. So identify the fact that it's an 8. So now I know I'm going to have some form of a negative out here. And I know that it's zinc. So I put my metal in. I put my parentheses ready for my ligand. My ligand is hydroxo, which is OH, and I have 4 of them. I'm not doing a very good job making that clear, am I? 4 of them. And so now do the algebra. 4 negative 1s is negative 4. The zinc is a +2, so what do you get when you have a negative 4 and a +2 added together? You get a negative 2. But I like to write 2 negative because that's the way it's done these days, and I've worked really hard to reteach myself that. I still slip up every once in a while, but I try. All right, so let's double check it. Tetra, 4, hydroxo, OH, zinc, with an 8 ending, means an overall negative complex. Zinc was +2, hydroxo's -1. Yep, we got it down. All right, so let's look at the next one. Notice the plus charge. So this is not going to be zinc 8, this is just going to be zinc. So zinc is going to end up in there, but I can't write to make it all smushed together, so I have to start at the beginning. I'm sorry. Tetra. Tetra. What's that thing called? Amine. Zinc. What's the Roman numeral for this zinc? It's got to be a 2, because 4 zeros, because this is 0, so 4 zeros, this has got to be a Roman numeral 2, plus you know zinc's always 2 anyway. And ion. What next? You should be pausing. All right, I'm going to pick up my pace, but you should be pausing in between these because I don't want this to take forever. So tetraamine copper 2 ion. So it's not an 8 ending, so it's going to be a positive complex. Copper is going to be here. Amine is going to be here. We used amine a lot in these examples because we know that's what's on the AP exam. A lot, as you will soon see. Put it in your brackets. And it's Roman numeral 2, so it's going to be a 2+ because I've got 4 neutral ligands attached to it. Now this thing you're going to make, when you do the equilibrium lab, if you have already done it or otherwise you will do it, you're going to mix 2 colorless solutions together and you're going to get this beautiful brick red precipitate, kind of orangey brick red. And you're going to do some color analysis with it because we can use a spectrophotometer or a colorimeter to be able to figure out concentration based on color using Beer's law and absorbance. You'll learn all that. Something to look forward to. So, we got to name this puppy. First of all, you need to recognize that as the ligand. Yes, it's not in parentheses, because sometimes the AP exam does that too as well. So we tried to mix it up a little bit on this lesson. So, how many of them are there? Just one. What is it? So I don't use the prefix mono. I start with di, which means 2, and go up from there. So SCN you should know as thiocyano. Because it's thiocyanate, but thiocyano when it's a ligand. So thiocyano iron. Now, this particular polyatomic ion has a -1 charge. That's a memory moment. You should know that. And the fact that this is +2 means this must be the +3 variety of iron. That's how you figure that out. And it's an ion. It's not in a compound yet. I'm going to have some compounds soon, but we're still doing ions. Matter of fact, the next one is a compound. Now we're going to take this ion and put it with chloride and make a compound. So this will be, it's still thiocyano iron 2, because it's a positive complex. Oh, Roman numeral 3, sorry. And I know it's Roman numeral 3 because, again, it took 2 chlorides, which I know are -1 each, so this has a +2, that has a -1, so this has to be +3. Thinking backwards. Reverse engineering. Oh, chloride. Just like you write sodium space chloride, we write thiocyanoiron Roman numeral 3 space chloride. All right, now shall we go to a different one? Cadmium, a new metal. And the charge on that cadmium is a +2. So CD, inside my bracket, open a paren for the tetraamine, so NH4 4 times, oh, NH3, sorry, got ahead of myself with my subscripts. All right, now that means this is a 2+ because the amine is neutral ligand. Doesn't matter how many they are, they're all still 0. Then what? Now I have another ion, and it's a silver ion. And so it's dicyano, 2 cyanides, which are -1 each, by the way. So that's a total of -2. The whole thing has a grand total of -1, and you know that silver's +1 anyway. So it is a negative complex. Do you see that? It's negative. Always be on the lookout for that. So this is argentate. Argentate. Does have a T in it, right? Ion. Oh, Roman numeral 1. I knew it didn't look right. Missed that part. Roman numeral 1. All right, then what do we have next? We have a compound. See, the magnesium's outside the complex, so it just starts off magnesium. Oop, I should change color for you, huh? Magnesium, and now we got to name the complex. Okay, so it's negative, but that's a typo. That should not be there. The fact that it took 2 of them right here means you should be able to deduce that it's a -1, but that negative really doesn't belong on the ion. So that's really just a typo. So I know that silver is a +1. I know that cyanide's -1, and there are 2 of them. That's how it ended up with a -2 charge. That's not right either. 2 minuses. Oh, maybe that minus does belong there. So it's an ion. No, it's not. There's 2 of them. Yes, that's why. There's 2 of them. Okay, I've done my math. Let me do that again. Sorry, I got twisted. All right, there's 2 of these ions. The ion themselves, AgCN twice, that's 2 -1s. Agreed? So that's -2 for the CNs and a +1 here. So this does have an overall charge of -1. But what we're doing basically is having 2 of them to go with the Mg, because Mg, you know, is 2+ in the 2A metals. So that's the story there. So we name it magnesium. Dicyano argentate Roman numeral 1. And that is a compound, so I don't put the word ion behind it. So that one you won't see on the AP exam, but again, I'm just trying to complete your education here. And then let's look at the next one. We have to draw this one. Oh, wow. Lots of dyes in there. I haven't seen that many I's in a word in a long time except for the word Mississippi. Okay, so dibromo, dichloro, diiodo, cuprate, 8 meaning a negative ion overall. Well, heck yeah, if you got 6 halogens in it, that's a -6 charge, with a +2 on the copper ion. All right, so we start with copper. We're going to need some room here. And then we have a triple ligand, all in the parentheses. And when you do the ligands, we name alphabetical by name, but we put the ligands in alphabetical by symbol. Isn't that fun? So let's say that again. Name alpha by ligand name, without regard for the prefix. But when you write the formula, alpha by symbol, ligand symbol. I'll put ligand symbol. It's more than you ever wanted to know, I realize. Okay, so we have Br, we have Cl, and we have I. Lucky for us, that is alpha. Okay, so Br, di-bromo, dichloro. There we have it. Close the bracket. -6 plus 2, total of -4. So 4 minus. Write that prettier. Because it's an ion. This is a compound, and it's going to end in chloride. So I have 5 amines and a Cl. So this one is penta-amine, because the word amine comes before the word chloro. Chloro, no prefix because there's only one of them. Penta-amine chloro cobalt. What's the charge on this cobalt? Well, it took 2 Cl's to make a neutral compound. So that means this is a 2- situation. I'm sorry, that's wrong. It's 2+ situation. And that means I had a chloride inside that really made this a 3+ metal. So one more time from the top. Do the math. The entire set of brackets is 2+. How do I know? Because it took 2 negative chloride ions to make a neutral compound. With me so far? 2+ for the whole bracket. Inside that bracket is a -1 for that, a whole bunch of zeros for that, and the question mark. So what do I add to a -1 to come out with a +2 on the whole bracket system? The entire complex ion, I have to add a +3. So this is cobalt Roman numeral 3. Chloride. And then I have potassium hexacyanoferrate Roman numeral 3. Alright, that just told me that the iron was +3. Hexa means there's 6 CNs, and potassium is outside of this whole mess. So K, I may have to put a subscript on that. Take me a second to figure that out. Hexacyanoferrate. So Fe, Cn, hexa, 6 of them, all -1s, that's -6. The total on this is going to then be, since the iron is a +3 and the cyan, or -6, isn't that a -3? So I'll need 3 + 1 potassiums to make that work. These are kind of fun. You have to admit it. It's like a big puzzle. Again, I have a compound. It's going to end in chloride. So my formula is going to end in Cl. We just don't know how many of them. Triamine bromo platinum. Okay, so bracket platinum. Amine bromo. So NH33 Br okay. The platinum is a +2. The amines are all 0. I've got a -1 right there for that bromine. So doesn't this thing overall have a +1 charge? Which means I only need 1 Cl to make that work. So it's correct as written. As long as I take the charges back off. And then, ooh, beastly. Okay, we have a chloro, a bromo, iodo, and an amine. How fun is that? All right, so we start with the amine because we go alpha by ligand name. So, and this is an ion, so I don't have a compound here. So I go amine, bromo comes next, di, bromo, chloro comes next, di, that's supposed to look like it goes together, chloro, iodo, iod, I-O-D-O-D-O, iod, that's not right. Stop right there. Iodo. Can you tell spelling's not my strong suit? Iodo. So I got them all. Amine, bromo, chloro, iodo. Copper. Now, the question is it copper 2 or copper 3? Well, let's do the math. 0, -1, -2, because there's 2 bromines, -2, and then the question mark. And that all totals up to -4. So, 2, 3, 4. This must be copper 1. That's the only way that's going to work. So this is copper 1. And the word ion. Because it doesn't have, it has a charge. It doesn't have anything behind it to make it a compound. All right. this whole complex must have a -3 because I needed 3 of those potassiums. This is -6 right here, so this cobalt must be +3. So this is potassium. Space, hexa, because there's 6 of them, fluoro, cobaltate. Cobaltate is how you'd really put the emphasis on those syllables. And Roman numeral, what did we figure out? It was a +3. And there you have it. Potassium hexafluorocobaltate, Roman numeral 3. Here again with the cobalt. And this cobalt must be Roman numeral 2. How do I know? Because I'm looking at the fact it took 2 chlorides, knowing that the whole bracket has got to have a +2 charge, and ammonia doesn't have any charge, so it's all on cobalt to carry the +2. So this one's hexaamine, cobalt, Roman numeral 2, chloride. And finally, iron, negative complex. I just don't know how much yet, but this is a +2. I know that because it tells me. And 6 cyanides. So this must be a 4- overall, right? Because that's -6. Yes, so 4- is its charge. And it should have had the word ion right there. That's another typo. All right. Now, I did that for fun, okay? If you fast-forwarded through it, you missed all the fun. But I don't want you to go away to college and not know some things you're expected to know just because the AP exam does not emphasize them. That's my motivation when I torture you like this. And I thought it was kind of fun anyhow. So now what you're about to see is much more encouraging. What you're about to see are all of the complex ion type questions that have been asked in the last 30 or so years, and you'll see that they're actually kind of easy. And the reason they're easy is you get some hints along the way. And if you practice a set, you'll be really, really good at this, I promise. It looks all scary and evil in the beginning, but it really is simple. We want to look for the words concentrated and the word excess, and if you see concentrated excess, that's pretty much a hammer hitting you over the head going, make a complex. You're in the land of complex coordination chemistry. So, again I say, what's the point? Well, stuff that doesn't dissolve in water often dissolves in either acid or base. So if I'm trying to take silver ion and get it back into solution out of silver chloride, well, silver chloride is a precipitate in water. So I need to try a base or an acid. And it turns out if I use a lot of concentrated ammonia, I can get my silver ion to turn loose of the silver chloride precipitate and get my silver ion back in solution. So I can do more labs with it. Plus it's darned expensive. Alright, so here we go. Concentrated ammonia. There's my first kind of hint that I might be in the land of complexes. At 15 molar is a big old hint going, good lord, that's mighty, mighty, mighty concentrated. 15 molar? So, concentrated ammonia is added to excess solution of copper 2 nitrate. Well, you know that that nitrate is going to be a spectator. So, this is really easy to get your product points. Remember, you get 1 point for the set of reactants set. 1 point for the set of reactants. So it's pretty easy to write Cu2 plus NH3. And an arrow. You get a point for that. And we're going to make a complex, and here is how you make them. See that 2 plus on that copper? You put your copper in here. What's twice 2? That would be 4. You're going to put 4 ligands. NH3, which is neutral, do the math. You have 1 plus 2 plus a bunch of zeros is going to be a 2 plus compound, or 2 plus complex, I should say. And there you have it. To balance it, I need 4 of these. So these are some of the easiest balancing you're going to do on the whole set. It's the payoff for this. So no matter how hard you might think they look and how scary they might sound, these are super simple. An excess of nitric acid solution is added to a solution of tetraamine copper 2 sulfate. So I'm going to have a spectator here and a spectator here. This becomes just H+. So H+ Now here's what I meant. You have to be able to decipher tetraamine copper 2, but you can do that now. You know what's going on. Start with your bracket, put your copper. Tetra, prefix meaning 4. What's inside the parentheses? Amine. And this is misspelled. That should be A-M-M-I-N-E. I never noticed that before. So NH3. See, it's spelled correctly down here. It's just a typo. Spell check sometimes keeps reverting back to 1M. And these are 2+. How come? Because it said copper 2 right there. So that's the charge on the copper. The ligands of ammonia are neutral. And so what's going to happen here? Well, if you add H+, so you put this stuff into acid, because it's not soluble in water. That's why it complexes. So if you put this stuff into acid, you're going to make, good buddy, ammonium. So make your ammonium ion. You're going to see this a lot, because you remember how much tetraamine showed up in our examples? It shows up a lot. So you're going to make ammonium. Sorry about that. Hit my mic. And you're going to release the copper, which is the point. Get the copper out of the complex. And it's still a 2+ copper. It's not a redox reaction. So to balance, I need 4 of those. And I need, how much in terms of, I need 2, no. I need 4. I need 4 of those as well. Sorry, it took all my fingers and toes to figure that out. Alright, so next, dilute hydrochloric acid is added to a solution of. Okay, so the dilute would throw me off, but hydrochloric acid, I understand, strong acid, H plus Cl minus, is added to a dilute solution of diamine silver 1. See, I know I'm in the land of complex just by looking at the name of that scary critter. So I'm going to have a nitrate as a spectator. I'm going to have a chloride as a spectator. So all I've really got here is take my acid and try to get silver out of this diamine silver 1 nitrate complex, or complex, no nitrate, just complex. So put your silver, open your parens here. They told you it's diamine. That means ammonia is in here. And it has a +1 charge. So there it is. Not the complex has a +1 charge again because of that Roman numeral. The silver has the +1 charge, and it's with neutral ligands. That's where that's coming from. Don't get confused by that. So what are we going to make? Well, once again, we have an amine and we have acid, so we're going to make NH4. Oh, I left my plus off up there. Sorry about that. Oh, and you know what I should also say? Well, I'll do it after this is finished. NH4 plus, I almost did it again. And the whole point is to get that silver ion back into solution and out of that complex. That's why you mix it in acid. All right, so let me say something about all along I've been trying to reinforce with you that a quick check for a balanced equation is if the charge is balanced on both sides. And so let's just make sure that you're clear that this still applies. So looking back up here at number 1, +2 on the left, +2 on the right. Looking at number 2, 4 H pluses is +4. 2+ extra for the complex makes total of +6 over here. 4 pluses is +4, and a 2+ is +6, so check, check. So far, so good. In the one we just did, I have 2+ on the right, and I have 2+ on the left. So we're balanced. So be sure you're double checking, because if you make a mistake, that's a fast way to find it and a fast way to fix it. If you focus on a charged species, if you have choices where some are uncharged, you usually can find your mistake pretty quickly. All right, solid aluminum nitrate. Aluminum is not a spectator at this point. You better know nitrate's a -1. You better know aluminum's +3, so thus you need 3 nitrates. It's dissolved in water. Now, at this point, I would be scratching my head, going, I don't see excess. I don't see concentrated. I see a solid that's super soluble, so why don't I just dissolve it? Because that's not the way these equations work. When you see aluminum, I want you to be suspect. Aluminum is amphiprotic. It often complexes with water. Amphiprotic means it can act as an acid or a base, but it's famous for complexing with water and hydroxides. So I'm going to complex it with water and free up the nitrate. So I put aluminum in here. What is the charge on aluminum, I ask you? Plus 3, you tell me. I say, what is twice plus 3? And you say 6. So double the oxidation number of the metal, put the ligand inside, and now do the math. 6 times a neutral ligand of water is 0. And so the whole thing bears that 3 plus charge from the aluminum, since it's with 6 neutral ligands. And now toss out your nitrate, which you know has a -1 charge. So the balancing comes with needing 3 of those and 6 of those. Total charge on the left, 0. Total charge on the right, also 0. We are balanced. Next, I have a suspension. We've talked about this word before. Suspension is different from saturated. So I have a suspension of copper 2 hydroxide. It's treated with an excess of ammonia water. So a suspension means that I have some suspended particles. So it's kind of code for solid. So you're going to put your copper 2 hydroxide down as a reactant, and then your ammonia. And by now you got to be getting a feel for the fact that we make a lot of ammonia complexes. Put in your metal, put in your ammonia. Copper 2, see that 2 right there? Copper 2, what's twice 2? 4. So a plus 2 for that copper, and 4 nothings gives a 2 plus total charge here. Agreed? Agreed. So what else? Well, we're going to just release the hydroxides. And I didn't mean to put that 2 there, sorry. I was getting ahead of myself. I like to do it in red for you. Alright, so I'm going to release hydroxide, but there will be 2 of them, indeed. And then I need 4 of these. Total charge on the left, 0. Total charge on the right, also now 0. Number 6, a solution of diamine silver chloride. Okay, we got a heavy metal bad guy in our midst here. Oh, not that color. Heavy metal bad guy. It's like OMG, except it's HMBG. So trouble, most likely, is treated with dilute nitric acid. So you're asking yourself, is the nitrate going to participate in this? No. So really we're just talking H plus here. But you have to realize that if you've got silver and chloride together, there's a chance you're going to make a silver chloride precipitate. So this is the complex. This is the last part that makes this not a complex ion, but rather a coordination compound. So let's get this down. AgNH3 twice diamine. This is a +1, that's nothing, so the whole complex is a +1. And that then is going to require some H+, and the Cl-, because the whole deal here is that it's the complex acting as a single species with chloride, and it is going to be soluble. Even though silver's in the complex, the chloride's not aware silver's in the complex. It's like it's locked up in a cage, or an unknown black box. But when it's released, let the precipitation begin. So we're going to make silver chloride. And then because we've got H+ in the presence of that amine ligand, we're going to make lots of NH4+ as well. So shall we balance? No, we need at least 2 of those. And that's going to force 2 of those because that's where it came from. 2 ammonias reacting with 2 H+. And I think the rest is balanced. Total charge on the left, +1. No, +2. Because there's a plus here and 2 more pluses here. That's +3 and a -1. So indeed, we are balanced with +2 on each side. An excess of concentrated ammonia solution is added to freshly precipitated, precipitated excess ammonia, copper 2 hydroxide. So that's an easy one to start with. Ammonia, copper 2 hydroxide requires 2 hydroxides. So what's going to happen? Well, we're going to make Cu NH3 4 times. I'm just going to swap this out and release the OH-. So it's almost like a single replacement reaction going on here. Now, what about the balancing? Well, I'm going to need 4 ammonias and and I'll release 2 of those. I need a charge. I missed my charge on my complex, didn't I? This is when you catch it, when you start doing the total charge business. So it's got to be a 2 plus because of that Roman numeral 2 right there, and the fact it's with the neutral ligand. So total charge on the left, 0. Total charge on the right is now 0 because I caught my mistake. Excess dilute nitric acid. Now the dilute part throws you off, but the excess, there's one of your clues. And it's nitric acid with an ion, so that's going to be a spectator, so this is really just going to be H+. It's added to a solution, tetraamine cadmium Roman numeral 2 ion. So H plus CdNH3, how many of them? Tetras, 4. Charge, 2 plus, because those are neutral ligands. What's going to happen? Well, for the, what do you figure? 6th time so far, we're going to make ammonium because we have ammonia in the ligand reacting with the H+. And then what? That's going to then bump the cadmium out by itself. So that puts it back into solution. So I'm going to need 4 of these ammonias to make that work. And I'm going to need 4 of these H pluses. So total charge on the left is +6. Total charge on the right is +6. Life is good. An excess of ammonia is bubbled through a solution saturated with silver chloride. Again, that saturated word means the silver chloride is there in a solid form. So you're going to write AgCl. So ammonia, NH3 plus AgCl solid yields a complex. Put your metal in. What is the charge on silver, I ask you? +1, you respond. What's twice +1, I ask you? 2, you respond. That's how many ligands you need. NH3. What's the charge again on silver with neutral ligands present? +1. I just told you that, you say with some aggravation. Cl minus then is released. So we need 2 of these. Take everything else? Yes. What's the total charge on the left? 0. Total charge on the right? 0. Life is good. All right. I'm going to need some room for this one. This one's a little bit trickier. I need a little more room. All right. Solid. Not tricky so far. Aluminum oxide. So can you write aluminum oxide? It's first time you ever learned a 2-3 trick, huh? Aluminum is +3, oxygen is -2, so I need 2 of the 3s and 3 of the 2s. 2-3 trick, I call it. And that's solid, and that's added to a solution of sodium hydroxide. It's only the hydroxide that's going to work out for you. But aluminum complexes with hydroxide, and so you may need some waters to make the whole thing work out. So I'm going to go ahead and put in the water. If you don't put in the water, you're going to get stuck, and your tactic when you're stuck is to put in the water. So what will I make? Let's make the complex first. Well, what's the metal? Aluminum. I ask you, what's the charge on aluminum? You say +3. Say, aha, then let's put 6 ligands on it, because what's twice +3? 6. What is our ligand going to be? Well, it's going to be the OH minus. So now what's the charge on this critter? 6 minuses and a 3 plus leaves you with 3 minus. All right, now, if we look at charge, I got 3 minus on the right and only 1 minus on the left. So my first thing is to get the charge balance and see, let the hydrogens and oxygens fall where they may. I can put anything in front of water I need to. Oh, you know what? I just screwed you up because I didn't notice that there's 2 aluminums. So let me do that first. I got to double this. Well, no big deal. It just means this goes to 6. Now what's the total charge on the left? -6. What's the total charge on the right? -6. Hey, we're good there. Now let's just try not to mess up anything with the charge. So let's try not to change the 6 or the 2. We got the charge balance because the other 2 things are neutral. So I got 2 aluminums, no worries. The O's and the H's get a little hairy. So I'm going to make a list, which I don't normally do, but I'm going to get lost on this one. Because I have 3 sources of O's on the left and only 1 source on the right. So I have 3 O's plus 6 O's plus an O, which I shouldn't write 0, huh? I should write 1. Isn't that 10? So 10 oxygens, and then I have 6 H's and 2 H's. That's 8. Where on the right, I have 6 of each. No, 12 of each, because I doubled it. 12 O's, because 2 times 6 is 12, and 12 H's. So how can I get to the right number of O's? I need 2 more. I've already counted this as 1, so if I put a 3 there, then this is no longer 1, this is 3, and that equals 12. Peachy. Oh, please let my H's work out, because what did it just do to the H's? This is no longer 2, right? Because originally that was my 2. I had 6 H's here, and now I have 6 H's here, and that's 12, and it worked. So that one was a little bit more beastly, and so when you get kind of stuck and stumped, it's not a bad idea to do this little tally thing you were taught way back in first year chemistry. It does come in handy from time to time. I'm just too lazy to do it every time. Because if the charge balances, 99 times out of 100, the whole bloody mess is balanced. All right, a concentrated solution of ammonia, so I'm thinking land of polyatomic ions, or I'm sorry, complexes. I'm going to switch to purple. Is added to a solution of zinc iodide. So that's just a spectator. So we have ammonia plus zinc. Make a complex. Put your metal in. I ask you, what's the charge on zinc? You respond 2 plus, because you memorized that. What's twice 2, I ask you? You say 4. And then I say, okay, that's how many of these ligands you need. Now do the math. What's the total charge on the complex? 4 times 0 is 0, plus my 2 plus zinc is going to be a 2 plus complex. Now balance it. There you go. Easy enough. Told you might like these once you learned it and got the hang of it. Now what? Excess of sodium hydroxide. Okay, so I'm thinking complex added to a solution of aluminum chloride. Chloride is going to be my spectator, so I simply have OH minus plus Al3 plus. It doesn't get any easier than this, folks. Open, put in aluminum. 3 twice is 6. Put in your OH minus. 6 minuses and a 3 plus is a 3 minus. Now you could also do the other most common. Aluminum makes 2 really common complexes. This one is actually more common. It's probably the one your book has more often. Like I said earlier, my disclaimer is you can double the oxidation state on the metal and make a valid complex. Not necessarily the best complex, but it'll get the job done. So I could make the aluminum, tetrahydroxoaluminate Roman numeral 3 ion is what the name of this one is. But have you noticed they're not asking you to name them? They're just asking you to sometimes interpret names. So that should lower your anxiety a bit. A concentrated solution of ammonia is added to a solution of copper 2 chloride. Spectator. All right, so what do I got here? I have ammonia and copper 2 plus. And so I'm going to make a complex that puts copper in here. 4 ligands. Ammonia. Do the math. It's a 2 plus. Balance. 4. Oh, I didn't balance this one up here. I need 6 there. Total charge on the left. I'm back up on number 12, sorry. Minus 6 plus 3 is minus 3. Total charge on the right, minus 3. I'm golden for this equation that I wrote. Right there. All right. Did I get this one balanced? Total charge on the left is plus 2. Total charge on the right is plus 2. Life is good. Excess concentrated sodium hydroxide. Ooh. We need a lot of base here, a lot of strong base. Is added to solid aluminum hydroxide. Oh, we're just going to take this. We're going to add a lot more OH to it. And we're going to make, whichever you want to make. You want to make the 4 this time because that'll be easier to balance. Aluminum. 4. It's a little far out there. You see why it's easier to balance? Ooh, I have 4 hydroxides on the left, 4 hydroxides on the right. Do the math. So 4 negatives and a 3 plus make that a negative overall. I have negative 1 on the left total charge, negative 1 on the right total charge, and I'm done. So sometimes that's an easier plan. And then let's look at excess concentrated ammonia is added to a suspension of silver chloride. We had this before. So how am I going to get this insoluble silver chloride to dissolve? I put concentrated excess ammonia with it, and it will let me recover my silver ion. It's going to complex the silver ion into this, which I have to do more steps to really get my silver ion back out. I should speak that properly. I'm going to complex it, which is going to get rid of my silver chloride precipitate and get it back into solution in this form. And then I think before we're done, we'll see the next step of this process where I really do get my silver ion out. All right, so I'm going to need 2 of these ammonias. And that's all I got. Total charge on the left, 0. Total charge on the right, 0. We are good. All right, let's look at the next one. Pellets, clever word for solid, of aluminum metal are added to a solution containing an excess of sodium hydroxide. Okay, you need to always be suspect of aluminum. Aluminum is amphiprotic, and it makes oxides, it makes hydroxides. You know, aluminum doesn't corrode well, and that's because it immediately makes an oxide coating as soon as it's exposed to air, or a hydroxide coating, whichever way. It's still got this impervious layer on it that won't let it react very well. So that's why you have to have an excess of sodium hydroxide if you want this reaction to go. It's an evil little question, I have to tell you. Way too complicated for anything that you'd see right now on the AP exam. But back in the day, when you didn't have to balance things, it was pretty straightforward. Just take some aluminum, add some hydroxide ion, and make a complex and be done with it because you didn't have to balance it. But when you have to balance it, you have to take into account reality, because I got to tell you, when I was making out the key, I couldn't get this puppy balanced, no matter what I did. And so I had to go to the internet, and I had to go find the industrial process. And so I want to share that with you, because it's actually kind of interesting, because it does have some impact on your daily life. This particular website, as you can see from the little URL up here, is in German, which would be the only foreign language I ever took in school. As a chemistry or as a science major at the university I attended, you had 3 choices. Latin, ooh, bad idea. If I were Catholic, it might have been a good idea, because I would have had some of that along my journey to college, but I did not. And then Greek was the other one. Ooh, really hard at my university. That was word on the street. And the third one was German. So that was the lesser of 3 evils. So I love the fact it says concentrated right here. They do percents, not so much molarities. This is aluminum, which is pretty much spelled aluminum, but then that's probably something to do with granules, or I'm guessing granules, because that looks like little granules. It doesn't look like pellets, but it's the closest I could find. So essentially what they have here is showing you, here's the aluminum metal. Here's what we're going to add to it. So then they've got a picture of aluminum immediately following the addition of the 40% sodium hydroxide. Not so exciting looking. They've put it down inside this beaker because this is going to be a very ugly reaction. And I mean ugly in a physical sense and ugly in a chemical sense. So after a while, about 2 minutes, they say, here's some bubbling that starts to happen. So you can see that a reaction is definitely taking place. And when you have bubbling, you got to figure out which gas is coming out. The usual suspects, when you've got nothing but aluminum and hydroxide, because the sodium is not vaporizing or anything, is that you're going to have either hydrogen gas or oxygen gas. So at the end of the reaction, there is a test tube in here. You can see its lip. You can see a little bit of the glass walls there. But this big, ugly, overflowing, foamy mess is what came out. And so it's a much more complicated reaction than it first appears in this net ionic simple little question. So they did a nice job of going on to explain what's going on here too. So they talk about the fact that they put 5 grams of coarse aluminum powder, which most people would call granules. It is combined with approximately 20 milliliters of 40% sodium hydroxide in a test tube placed in a 2-liter tall glass beaker. Then a violent reaction causing gas production begins, and an oxyhydrogen gas probe returns positive. So it was trying to pick up if you had oxygen or hydrogen gas present, and it came back, well, yeah, you got one of them. So under normal circumstances, the aluminum does not react with water, again, because there's an impermeable protective layer composed of aluminum hydroxide, which either forms within seconds or is already in place. But with the addition of the sodium hydroxide, that layer is prevented. So it coats the aluminum and doesn't let the water vapor in the air react with it to make the coating that protects aluminum. So with the production of aluminates, which is what they call this aluminum complex with the 4 hydroxides that we've seen over and over, The amphoteric, and they go on kindly to define that that is capable of acting as either an acid or a base, aluminum hydroxide, goes into solution. So make no mistake that the first thing that's going to happen is aluminum is going to react with the water and make aluminum hydroxide. And the bubbling that you see is because of hydrogen gas coming from taking hydrogens off of the water to give us the hydroxide ion. But with excess sodium hydroxide or very concentrated sodium hydroxide, that compound that forms first is going to further react to complex into the hexa aqua alumin 8 Roman numeral 3 ion. Alumin 8 because it's a negatively charged ion. So as we keep going on, then we actually are going to end up making some aluminum oxide. So it says a layer of aluminum oxide previously formed by the passive corrosion is also dissolved by the addition of sodium hydroxide. And so that's what, for that reason, that the reaction takes place at the beginning relatively slowly. That's why it took a couple of minutes before they saw anything going on. So we have this reaction going on as well. So the aluminum is completely dissolved at the end, and water acts here as an acid. And this is the reaction that Drano uses. Have you ever heard of Drano? Ever had a clogged drain at your house? Ask your parents about Drano. A lot of people opt for liquid Drano now because this stuff can get nasty. This is the powdery stuff is really nasty. So what you get going on here is that we have strong alkalis. Well, alkalis work well because they're polar. On polar things, but they also work well on organic, like fats and greases, and hair, which is a big giant protein. So aluminum or zinc is added into these strong alkalis of potassium or sodium hydroxide, and those alkalis, like I said, break down those organic residues, but they also form hydrogen gas as a byproduct. So that bubbling of the gas formation gives you some mechanical cleaning action, which helps break up the clog. So it's just, kind of interesting, but I have to tell you this is an evil equation. So let's do it. Okay, I have some aluminum, obviously, the aluminum metal. We're going to have loads of OH minus to work with, and we need that water. And that's what was not obvious to me in the beginning. So what we're going to make then is the AlOH 4, or you can make 6, just whichever one you want, just got to have to balance whatever you do. I chose 4 this time. Plus hydrogen gas, and that again was a part that I was not thinking about. So I tried to balance this simply and couldn't get it to happen, so I had to go look it up. So there's our net ionic reaction. Those are our players. So I see that I've only got one charged species on each side, and it has a negative charge no matter what I do. So when I look at this, I've got to figure out whatever I do to the aluminum hydroxide thing, I've got to do the hydroxide thing. That's just a given. So at first, you may try to just go with the H's and the O's. And so I'm going to make a little list, which I don't always do, but it's very helpful when it gets complicated like this. All right, I've only got a source of one H and a source of 2 H's on this side. I have a source of 4 H's and I have a source of 2 H's on that side. For my oxygens, I have a source of 1 and I have a source of 1. And then I have a source of 4, and that's all I have to work with. So I've got to figure out what to do here. If I put a 3 here at first, thinking that'll work with my O's, then I get into hydrogen trouble. Because now I've got 7 hydrogens on the left, because this is no longer a 2, now this just became a 6. So I have 7 hydrogens on the left, and I can't put anything here to go with the 4 to get 7 because these come in multiples of 2 in the hydrogen molecule. So when that happens, I think, all right, let's double the scary looking thing. That's always my tact. And that forces a 2 there. And it's going to force at least a 2 here. And if not, then I'm going to have to come and do something else, because that charged species is what's giving me the most grief on this. I've got to stay balanced by charge on both sides. So let's try again and see what happens now. So this just became 2. I've left that. I'm going to go back to my source of 2 here, because I took the coefficient off of there. Over here is now kind of a mess. I've got 8 and 8. You see it? 4 O's, but double it. So that's 8. 8 and 8, right? 4 O's, but double it, that's 8. 4 H's, but double it, that's 8. And then I have a source of 2. That's the wrong place. Sorry about that. I have a source of 2 up there on the hydrogen. All right, so how could I get something to transform into 8? If I put 6 here? Did I do that right? Oh yeah, because I can put anything I want in front of H2. Okay, so let's focus on the O's first. What do I have? I have now 2 here and 1, but I have 8 O's over here, so that's troublesome. So without goofing up my hydroxide and goofing up my charge, let's see what we can do with the water. If I put a 6 right there, so this is now a 6, that makes 8 on each side, okay? Peachy. So I now have, how many, I got my O's sorted out. How many H's did I just introduce? My 2 now becomes 12. I'm up to 14 on that side. Is that right? I'm up to 14 on that side? Yes, yes, yes. Okay, so how can I get to 14 on the other side? Well, I have 8 and a source of 2. If I triple that, I have 6 and I have 14 on both sides and the charge is balanced. Evil, evil, evil. Not going to happen to you on the current AP exam. That's just too mean. We wouldn't do that to you unless we gave you loads more information and took it out of this section where we gave you the equation, maybe had you balance it. That might be about as evil as it would get, but you'd be given all the players instead of having to come up with the whole thing from scratch. Whew, glad that one's over. A suspension of zinc hydroxide. I don't want red. Suspension of zinc hydroxide is treated with concentrated sodium hydroxide solution. Again, I'm going to have spectator because I don't have a heavy metal here. I can do that. So ZnOH twice plus the hydroxide. I'm just going to complex this. So aluminum and zinc do this. They make these complexes. And if I double zinc's 2 plus charge, I get 4 ligands, 4 minuses, and a 2 plus, giving me a 2 minus charge overall. So I need 4 here, and I'm back in the exact same boat I was just in. I've got 4 OHs. Oh, no, I don't. This one worked. Hey, is that what I did wrong up here? No, because they gave me aluminum metal. Okay, never mind. Thought I just got a saving grace there, but I didn't. So 2 minus, 2 minus, we're done. That one was easy. That's the way it's supposed to work. Next, I've got silver chloride is dissolved in, implies it was a solid, in excess ammonia. Are you tired of this equation yet? Probably not, because now you're getting it. Ag, NH3 twice, because Ag is a +1 metal doublet. Get 2. So carries a +1 charge because the ligands are neutral, and we free up the Cl minus. So a little while ago I said eventually I'm going to get my silver out of here. This is where I thought that happened, but it hadn't happened yet, has it? Do I have another one? No, maybe I don't. Maybe I don't have that step on here. All right, sodium hydroxide added to a precipitate of aluminum hydroxide in water. Spectator, because I don't have a heavy metal present. I do have a precipitate of aluminum hydroxide present. So make your complex. Make it easy on yourself. Which one do you want to make? I'm going for this one. With a -1 charge. 4 minuses and a 3 plus. Total -1. Alright, then what? A drop of potassium thiocyanate. That's SCN minus. Potassium's going to be a spectator. Is added to a solution of iron 3 chloride. So I simply have what takes place in that equilibrium lab. I have SCN minus plus the iron 3 ion. And this is an exception to that whole coordination chemistry rule thing, because this is lab. You should know this one. Now, I think if you do the formula and you put 6 of them in there and you do the math right, you would still get all your points. But I want you to embrace the fact that you should know this one. This is lab. This is the classic KEQ equilibrium lab. If you haven't done it yet, you will. This is where you mix 2 colorless solutions and you make this orangey brick red solution that we can use a spectrophotometer or a colorimeter with. All right, concentrated solution of ammonia. Getting used to that now. Added to a suspension again of ZnOH2. That means there's solid present. So take your zinc, put it in the complex. Its charge is 2. Double it, you get 4. Put the hydroxides in. Oops, no, you're trying to get the hydroxides out. Put the ammonias in so you can get the hydroxides out. Again, it goes back to the fact that this was a solid, so we're trying to dissolve it, and water didn't work, so we're going to try ammonia. And indeed, we complex the zinc to get it into solution in a complex and release the hydroxide out of that solid. So balance it. How many hydroxides? I had 2 on the left. I have 4 of those. Total charge 0. Total charge 0. Life is good. That's the way it's supposed to work. Excess concentrated potassium hydroxide solution. Excess concentrated potassium hydroxide solution is added to a precipitate of zinc hydroxide. Didn't we just do this basic? Oh, now we're adding the hydroxide. Never mind. So this is just going to make a bigger complex. So 2OH minus plus ZnOH2. All right, in lab, this is a precipitate. It's insoluble. But if you add more hydroxide to it, you can actually get the precipitate to dissolve. Notice I didn't say disappear. This is not magic. But if I keep going, and this is a bad thing if you don't know about this, because that could happen accidentally, and you could be doing a lab where you expected the end product to be a precipitate of zinc hydroxide, and it never shows up. If that happens to you, back down the concentration of the hydroxide and try again. You may be flooding it and really pushing this to make the complex when it's not what you desired. A solution of ammonium thiocyanate is added to a solution of iron 3 chloride. Here we go again. And normally the ammonium, this would trick you, and you would think, okay, I'm going to use the NH4 and I'm going to put a complex over here with ammonia. But you have to know that thiocyanate and that iron 3, and you should because of the lab that you've done, or will do, depending on what time of year you're listening to me. And there you have it. Easy enough. Total charge on the left, plus 2. Total charge on the right, plus 2. And, drum roll please, this is the last one. Excess sodium cyanide, spectator, added to a solution of silver nitrate. That's why that's a spectator, because it can make sodium nitrate soluble. So we're talking about taking cyanide and mixing it with silver ion. This has danger written all over it. And it makes a complex of AgCN twice. Do the math. Why did I put 2 of these? Because Ag is a +1. I put 2 of those, double the oxidation state, and so I'm going to end up with a minus overall. And that, ladies and gentlemen, is what we call a wrap. Apologies for the one that I couldn't get to balance right. I'm stubborn enough to investigate that, so I may tack on another few. Forgive me, let me have a do-over moment to the end of this recording after I go look that puppy up, because for whatever reason, my brain's not capable of balancing that one. But hey, I got 23 out of 24. Good enough to make 5. So I hope you now have a bit of fondness for these and know that they are easy. Do not fear them anymore. I have sent you before to this site. This is the Net Ionic Equation Practice site. And David Brooks at the University of Nebraska at Lincoln has developed the site for AP questions. And the nice thing about this site, you definitely need to go out there, is it asks you the little question aside from just focusing on being able to write and balance the net ionic equation. What I've been doing with you would get you 4 points, 4 points, 4 points, but you want 5 points, 5 points,